Hello, everyone. Welcome back to this week's algebraic graph theory seminar. So first, I have an announcement is that next week will be one of our special time seminars. So it will be 6 p.m. Local Waterloo time. So I will let you to figure out what time it will be in your time zone. And the second, like you see inside, is our 100th talk today. So today, we have Paul Horn to talk about the graphs on curvatures and local discrepancies.
So thank you very much. It's absolutely a great pleasure to be giving a talk here, and thank you very much to Sabrina for inviting me, and for all of you for coming. And it's nice to see a number of familiar faces, especially Fan. It's very nice of you to come quite early in the morning for you and join us here. And it's also quite an honor to possibly be the 100th talk in the seminar. There was quite a bit of discussion back and forth. So I guess officially maybe I am. And so it's perhaps a hard talk to have the 100th talk in the algebraic graph theory seminar, when what I really want to tell you about is analysis and to ruin the room. But I hope that it will still be interesting and enjoyable for you. So again, thank you very much. And so let me set up what it is I want to talk about. And I mean, it's a graph theory seminar, so far I haven't missed the room. I want to understand graphs. We all know what graphs are, vertices, edges, whatever. And we know that, you know, if I have something small and simple, perhaps I can understand it explicitly. I am trying to move some zoom a little bit here so I can see what I got. But if I've got something more complicated, if I've got a graph perhaps arising from the real world, it's a much more complicated challenge to understand such a graph. And so I need some mathematical tools to do such. And unfortunately, many of the things that you might want to know about large graphs, as I'm sure that the audience here is extremely familiar with, it's a lot of things that you might want to know are extremely computationally difficult to figure out, especially if you want exact answers, sometimes even for some approximate answers, and especially considering the overwhelming size of many of the large networks that you're interested in understanding. And so one thing that you might want to do is perhaps weaken your aims a little bit, not understand a large graph exactly, but rather be able to more cheaply certify that your graph has some properties that are of interest to you. And in particular, I'm interested in kind of large-scale geometric properties, things dealing with their diameters and cuts and bottlenecks and things like this. And how can I recognize those quickly? And now we get to the part of the talk which is at least on brand for an algebraic graph theory seminar. The one way to go about doing this is through spectral graph theory. So associate matrices with a graph, look at their spectra, and try and understand things. And I think have to tell this audience that probably the most common way of doing this is via the adjacency matrix. The adjacency matrix is particularly nice for regular graphs, where you can explicitly understand, I know what the largest eigenvalue is. It is the degree. I know what the eigenvector corresponding to that degree is. And I know that if there is a gap between the first and second, this really should be 2, I apologize for that. But between the first and the second eigenvalue, implies that a graph has many nice properties. And On the other hand, this first eigenvalue is closely related to, say, walks in my graph, even if I'm not regular. This lambda one is still telling me something about how many walks of length k there are, kind of asymptotically. So this is a wonderful matrix, but there are others that people use. The next one I'll mention is the combinatorial Laplacian, which is another one that is quite familiar here. And I'll mention, because I want to talk a little bit about geometry later, that this is also closely related to the combinatorial Laplace operator, which for reasons which I will admit I don't fully understand, there's a sign change actually between the Laplace-Beltrami operator, which is non-positive semi-definite, and the combinatorial Laplacian, which is positive semi-definite. So in order to get results that look a little bit more like the results from geometry, one often changes the sign here. And I will use delta to be this sign changed Laplace operator. All right. And there are many things that you can tell from these. Kind of right away, these eigenvalues tell you something about the connectivity of your graph, or at least the number of components. The first eigenvalue is always 0, and the number of zeros are the number of components. And as kind of a quantitative version of that, perhaps, you have the matrix tree theorem, which tells you that these eigenvalues can actually count for you spanning trees in your graph. Of course, having more spanning trees, in some sense, you can say, well, that's being more connected. And so in some kind of way, these eigenvalues are telling you something about connectivity, how many spanning trees you have, etc. It's not graph connectivity in the sense of how many edges I remove, but it is still some kind of robustness that this is telling you about. There are other matrices as well. Fan is here, so I would be remiss if I did not mention the normalized Laplacian, which is, again, it's a normalized version of the combinatorial Laplacian. So I'm normalizing it by the degrees. Here I'm taking the combinatorial Laplacian and I'm normalizing it in a symmetric way based on the degrees of vertices. There's another version of this normalized Laplace operator, which is no longer symmetric, but it is similar. Well, at least that's with this sign change, it's similar to minus the normalized Laplacian. So even though this is not symmetric, it has real eigenvalues because it is similar to this symmetric matrix. And in fact, the eigenvalues are the same as the normalized Laplacian up to this sign change. And so in some sense, they're giving you the same information. And you can here really see that this matrix is going to tell you a lot about how random walks behave on your graph. You can see the transition probability matrix for the simple random walk sitting there and staring you in the face right away when I have it in this form. All right, now for this matrix, it's been normalized, so now the eigenvalues live between 0 and 2. Again, the number of zeros is telling you the number of connected components. So if you always have this eigenvalue of 0, and if the next eigenvalue is separated from 0, then you're connected. And the largest eigenvalue is telling you something about bipartite pieces. So the number of bipartite components of the number of 2's. And in some ways, this normalization for degrees allows it to work a little bit better for irregular graphs than the adjacency matrix. You can recover some of the same kind of results you can for regular graphs, you can recover for all graphs using this matrix. I want to mention a few of particular importance and particular interest as we go through here. So perhaps the most celebrated result that you get easily from this normalized Laplacian is what is known as Cheeger's inequality. So Cheeger's inequality relates an isoparametric property of my graph. That is how easy it is. It is a measure of a normalized cut. So I'm looking at comparing how many edges I have to cut off a piece versus how large that piece is. So that gives me kind of a normalized cut. And then this lambda1 is sandwiched by this property in both directions. So in other words, if this first eigenvalue of the graph is small, then I have a fairly sparse cut that is there, and vice versa. So it bounds it in both directions and is quite nice here. And I like to think of it as kind of a quantitative statement, version of this statement, that the number of zeros appearing as an eigenvalue is the number of connected components, because really what it's telling me is it's telling me that if in fact this first eigenvalue is separated from zero, this first non-trivial eigenvalue is separated from zero, then actually I'm quite well connected. So not only am I connected, but the bigger it is, the more connected I am. And I should mention, again, this is perhaps in the wheelhouse of people here, but I want to highlight it anyway, that Cheeger is no graph theorist, and this result did not originate in graph theory. In fact, it arose in differential geometry, where for this lower bound, there is almost an exactly analogous statement where this lambda1 now is an eigenvalue of the Laplace-Beltrami operator in the manifold. And the isoparametric constant, this phi, is defined to be a measure of the volume of a piece you cut off compared with the area of the boundary. And you really get the same behavior. This other bound, this upper bound for lambda1, it's quite easy. It's a very useful bound in some sense, but it's very easy because lambda1 is the solution to a minimization problem, and all I need to do is take this cut and exhibit some vector that bounds the Rayleigh quotient in some nice way. And it's somehow very easy to get this upper bound for graphs. And it's not part of what is known as the Cheeger inequality in geometry. There's a more complicated inequality in geometry, actually, which is known as Booser's inequality. It's a little bit more complicated even than what I'm giving it credit for. But the main thing that it says is that if you have a non-negatively curved manifold, then actually the lower bound of Cheeger inequality is tight. That you'll get both upper and lower bounds of this form of phi squared for non-negatively curved manifolds. If you have a curvature bounded from below, then you get some linear term. All right. I should mention another thing, which is commonly referred to as this expanded mixing lemma, although I think Fan would be mad at me if I didn't say also that it's often called the discrepancy inequality, and actually that's kind of what I'll call it later, but this really is a very common name. So another result that one gets quite easily from the eigenvalues of this normalized Laplacian is a bound on discrepancy, which is to say a bound on the pseudo-random properties of your edge set. So what this is really saying is that if I look at the edges between subsets, and I compare it to what I would expect in a random graph. So this would be the number of edges I would expect between these sets if the degrees were the same, but all edges were distributed randomly in, say, the configuration model or something like this. Then I get an upper bound, and this upper bound is based on how close the non-trivial eigenvalues are to 1. So it's a little bit hard to perhaps visualize this, but again, what's actually going on here is the eigenvalues are between 0 and 2. And so this is kind of looking at how in the middle they are. And if they're all kind of in the middle, then you get tighter and tighter bounds on this. And there's a version of this for regular graphs, that one gets from the adjacency matrix. But again, this can kind of be extended to all graphs using the normalized Laplacian. So it's one of the important parts of the spectrum of this graph, or the spectrum of these matrices, is that they're telling you something about the pseudo-random properties of your graph. Okay. And like this pseudo-randomness kind of touches on a lot of things, and it's extremely useful in a lot of places. So Fan, along with Ron, Graham, and Wilson, back in the 80s, introduced the notion of quasi-random graphs. They showed that a number of properties held by random graphs are actually deterministically equivalent. So that if you had a sequence of graphs that had some properties, then actually they had a whole suite of properties that were shared by random graphs. And perhaps one of the easiest to certify, most useful of these, was actually the eigenvalues. So if you have a sequence of d-regular graphs whose lambda 2 is literal 1, then actually this entire family will share many properties of random graphs that, as I say, they all turn out to be equivalent. And one thing that you can think of as almost building on this, but more broadly, is the regularity lemma. The regularity lemma says actually all large dense graphs can be broken into a bounded number of pieces, where between which I get bipartite graphs, and these bipartite graphs are pseudo-random in some sense. And from here, I get all sorts of nice consequences from this pseudo-randomness. Expansion, I can count subgraphs. There are bounds on diameters and distances. And there's a theme here that somehow random graphs are perhaps paradoxically easy to understand, right? And so this spectrum gives me a guarantee on how random a graph looks. And from that, I can actually understand quite a bit because, again, random graphs are easy to understand. All right. So I want to switch gears a little bit, and I want to get to the second part of my talk, or the second word in my talk, and that is I want to talk a little bit about curvature. And now I'm a graph theorist at heart and not a geometer. And so I'm going to insult any geometers in the room by kind of oversimplifying curvature just a little bit. but so that we can get ourselves in the same headspace. So curvature is on a manifold it's a local measure of expansion. So a manifold kind of locally looks like n-dimensional Euclidean space, and the curvature is measuring how it is expanding compared with that n-dimensional Euclidean space that it looks like. So if you have a flat space, then the kind of local expansion of balls as you go out looks just like it does in Rn. If you're positively curved, for instance, on a sphere, and you take a little thing, it's kind of closing in on itself, so it's a little bit smaller than that. Negative curvature will be expanding faster than that. And if you have a manifold that has some kind of curvature bound, then you get all sorts of geometric and analytic consequences. So from curvature lower bounds, you can get kind of analytic consequences. I'll mention one of them here, which is a bit of an acquired taste, but for instance, you get this so-called Bochner formula or Bochner inequality that tells you that if you have an n-dimensional manifold with some curvature lower bound, then if I take, so I have some, then, if I have some function, calculus works on it in a particular way so that the Laplace of the gradient is bounded below. And it's bounded below by some terms, and the curvature shows up here. So for instance, if the curvature is non-negative, then this term vanishes. Okay, so it's a bit of an acquired taste, but it's still going to be useful for us. Now, curvature is really, it's taking a derivative or a second derivative in some sense. I'm looking at how things change as I go out. And it's hard to take that definition and apply it directly to a discrete space like a graph. So there's been a number of notions introduced recently to try and define a notion of curvature for a graph that is useful. It's a measure of local expansion. So the first kind of thing you might think of is something on degrees. The problem with the degrees is they're not quite coercive enough. Like I can have a lower degree bound and I can have graphs that look a lot of different ways. It doesn't give me that much information, but it's still the first idea. And it's local at least. Other notions that are a bit more sophisticated have tried to take this local notion, degree, and kind of build it out a little bit. So there are notions based, for instance, on the transportation or Wasserstein distance that are based on how well you can couple random walks that start nearby each other. If you have a graph that kind of closes up on each other, then you can couple local walks together, or couple random walks together. Well, if your graph is more tree-like locally, then you just can't couple them as well. And so this is a more positively curved thing. This is more negatively curved. It's just branching out. And so the better you can couple the random walks, the more positive your curvature. And you can make this quite precise. And you can also look at satisfying some analytic condition like this Bochner formula. And I just want to point out, you have this Bochner formula. It's some, as I say, very much acquired taste where you have Laplace and you have gradients and you have all sorts of things. But actually, it was already noticed by Bochner and Emery some time ago that this can be used as kind of a definition of curvature in many settings, especially when things are well behaved. So especially when you have so-called diffusive semigroup, essentially when the Laplace operator satisfies the chain rule, which unfortunately it is not for graphs, but okay. And actually, satisfying Bochner-like conditions has been shown to imply many nice properties of graphs. So with Frank Bauer, Yang Lin, Gabor Lipner, Dan Mangubi, and SDL, a few years ago, we proved an analog of the Li-Yao inequality for the diffusion of heat. And so it kind of begs a question whether there are other analogies between curvature and which is somehow it's locally defined on a graph, and eigenvalues which are more global. And all of these, as I say, are very analytic. So one might wonder whether you can actually take this very analytic technology and try and get something more combinatorial out in the end. And that's what we've been interested in doing. All right, so let me give a little bit more background here. So we have I'm going to be using just the standard combinatorial Laplace operator here. And for instance, this is how it acts on a vector looking at a point. And so one can actually then define the gradient, or at least the inner product of a gradient in itself, using essentially the product rule. And if you work this out for a graph, then you get something that very much looks like the gradient of f dotted with the gradient of g, where now the directions are the different edges coming out. So I'm looking at the difference of these vectors across each edge. This is how it works out, but it works as a nice definition. And from here, you can just define the curvature dimension inequality, which is to say, I look at this Bochner formula, and I ask for which k at a point, what are the best k I can write there? And I'll say that a graph satisfies this curvature dimension inequality if I can write down a k and put it there. Solve it. For instance, every graph satisfies a CD with some dimension, some curvature. But there are flat graphs. Among these are very naturally ZD or abelian Kelly graphs. For instance, Chung and Yao some time ago introduced a class of Ricci flat graphs, and these, well before people started using these definitions, but these turn out to be flat as well. It's a local property. That means I need to check distance to neighborhoods of vertices. Now, this is both a bug and a feature in the sense that if you have something like the hexagonal lattice, which is arguably flat, it looks locally like a tree, which is negatively curved. But on the other hand, it only depends on distance to neighbors. So it depends on a Laplace, which goes out one step, of a gradient, which goes out one step. So this really just looks at the second neighborhoods and defines something here. I'm going to go quickly over this because I'm going slowly, but this is the idea of Ricci flat graphs, which are trying to mimic a lattice property. All right. So this discrepancy inequality, the expander mixing lemma, as I said, it looks at the eigenvalues of the normalized Laplacian and how they certify the randomness of the graph. And it's at the most in bulk that if I have like a reasonably dense graph and I have fairly large sets, then it measures the number of edges between them compared with what I expect in a random graph. And although I don't need the full force of it, it does sort of that somehow a Cheeger type inequality is enough. It certifies some kind of expansion in small diameter. Curvature says something a little bit different. I mean, on its head, it's certifying something about local neighborhoods. It's looking just at distance to neighborhoods. And actually, it's saying something about the opposite of expansion. It's because it turns out that non-negative curvature implies that polynomial volume growth, and it's a result of Florentine-Munch that if you have a graph with non-negative curvature and kind of bounded degree, it's not an expander, it's somehow the opposite. So in some sense, it's saying something, as I say, quite opposite. All right. And somehow the takeaway from this is curvature doesn't control global discrepancy. That there's no way I can take some curvature bound and take big sets and look at the edges between them and say that there are a lot of them, because that would right away say that I have kind of some kind of expansion. I have some kind of really small diameter expander. And I don't have that from a curvature lower bound. However, it doesn't control the edge distribution globally. It does turn out to control it locally in the following sense. So again, this all has to do with so curvature of itself is looking at the distance to neighborhoods in my graph. And so one thing that you could ask is you could take a vertex, its neighborhood, its second neighborhood. You could split up the first neighborhood. And I could ask, how does the second neighborhood interact with the first neighborhood? Well, what I would kind of expect on a broad level is that the vertices up top, if everything were distributed randomly, they would be sending about half of their edges to one side, about half of their edges to the other. Now, this very much depends on how I choose to cut this, at least for any given vertex. So if I have a vertex, of course, it has kind of low degree down to this first neighborhood. I can choose a cut that is kind of on one side or the other. And this last little schematic slide is suggesting that actually maybe a little bit more is true, that if I cut up my first neighborhood like 10% on one side and 90% on the other, I expect more or less 10% of the edges from up top to be going to one side and 90% to the other. And all of this was perhaps a little pie in the sky, but it turns out that something along these lines is very definitely true. Unfortunately, the result is a little bit ugly, but let me try and highlight the first bit. I have it, yeah, okay. Anyway, so what is all of this saying? I'm going to call this a discrepancy inequality. So what is really going on here? I'm taking my graph, I'm taking a vertex, I look at the first neighborhood, the second neighborhood, and I'm going to cut the first neighborhood up. So I'm partition the first neighborhood into two pieces, x and x bar. And now suppose I have an alpha 1 minus alpha split. Then what's going on here? This is a quantity which would be 0 if the degree of z was split in exactly the way I wanted it to be. So I look at a vertex in the second neighborhood, I look at how it splits into z and z bar. This would be 0 if it's split exactly according to this random distribution that I want. Generically, it won't be 0. And generically, I will have something. However, on the bulk, I get something. On the bulk, I get an upper bound for this quantity when I go across all edges. And I get a quantity that the higher the curvature, then the more pseudo-random in the sense that it looks. The more the vertices in the second neighborhood will split, at least in bulk, to the first neighborhood. On any way I partition that first neighborhood, the more random that it will look. Unfortunately, there's some other terms here. They're in a sense unavoidable. Some of them vanish. For instance, if you have a triangle free graph, things are a little bit nicer. But this kind of discrepancy inequality, as I said, again, this is a measure of how random I look. And the bigger this is, the more my vertices are tending towards one side or another. And this is governed in a way that the bigger the curvature, the better it looks. And as I say, so this turns out to be sharp for some classes of graphs. It gives a bound in exactly the direction that we kind of wanted here. So it is saying that when I have a graph, the higher that curvature is, the more random the edges between the first and second neighborhoods look. Is already quite nice. I will try and bring it back down to earth because this is a little bit of a weird inequality. One consequence of this, for instance, from the expander mixing lemma, a very useful consequence, this is stated for regular graphs here, that the number of edges between S and its complement is at least something. So if you solve this, you get some D, lambda, whatever, S and S bar. And actually, you get somewhat of a similar result here, that if you partition actually here the second neighborhood into two pieces, let's see. Oh, excuse me. This isn't the second neighborhood. This is the entire ball of radius 2 into two pieces. Then you get something that looks at least somewhat similar in the way that it's acting. So this is could be thought of as a kind of Boozer inequality. It's some kind of again measure of local expansion. Another kind of nice aspect of this is that it's in some sense talking about how the balls around points, these radius 2 balls, are stitched together. So, I mean, one thing that you might like is to take this ball around a point and say, oh, it's actually quite well connected. Perhaps it's 2 connected or more. And actually, even under positive curvature, this isn't necessarily true. However, what one can prove is that if you have a graph which satisfies one of these curvature bounds, and this K is not too negative, that is, then, well, you don't quite get 2 connectivity, but you get that the ball removed the center is connected. And this actually improves a result of Cushing-Lewin. I can't pronounce his name, and I apologize to him. It's not going to happen this morning. But it improves the result where they showed that if you were non-negative, you got this. Another kind of nice consequence of this is that you get a connectivity bound for your graph based on this. Well, almost. It's kind of a funny thing about curvature. Curvature is very, very local. And therefore, curvature can't actually tell whether your graph is connected or not. If you have a graph that has some positive curvature and non-negative curvature, and you take two copies of it, two disjoint copies of it, locally, all the neighborhoods look exactly the same as in one copy. So curvature cannot tell whether or not the graph is connected. However, it turns out that using this kind of local discrepancy, you can actually show that if you have a connected graph, you're very connected. And you're very connected in a way that depends on this curvature. And again, the more connected you are, the higher your curvature is, then the more connected you are. Yeah, so as I say, curvature cannot certify that a graph is connected, but it can certify that a connected graph has high connectivity. And of course, this is tied to this very classical bit that Spectral is really allowing you to lower bound connectivity. I will mention that another thing that you get from this kind of pseudo-randomness, for instance, is counting graphs. So in particular, if your graph is quasi-random, then you know that it has the same number, or graph sequence is quasi-random, then you know that the subgraph count of kind of all graphs are that you would expect in a random graph of that edge density. And of a particular importance in this is the role of 4 cycles. 4 cycles are particularly important for quasi-randomness because having the right edge density and the right number of 4 cycles from a random graph actually forces your graph sequence to be quasi-random. Here, you can prove something of a little bit of a variant of this discrepancy inequality that allows you to actually count 4 cycles. And again, this is very similar to something that you would get from the graph spectra. This is allowing you to bound the number of 4 cycles in triangles at a vertex. This is, what do I want to say? So this is doing somehow the same thing using curvature locally. Finally, I'll mention all of you have very politely sat through the entire talk, so I should mention something about strongly regular graphs. And then if I mention strongly regular graphs at the end, perhaps you'll all forgive me for the preceding 50 minutes. So let me mention something about strongly regular graphs. There's a conjecture that strongly regular graphs of growth 3 actually satisfy this kind of curvature condition with positive curvature, with curvature 2. Now, it turns out that one can show that this conjecture is false if you have one of these strongly regular graphs with parameters nd lambda 1 exist for some lambda positive. As far as I can tell, and of course people here are much more expert than me, this is still open and has been open for quite a while. I don't even know what the betting markets are on it. Is it supposed to be false that they don't exist? That's somehow my broad impression. But anyway, if these happen to exist, then this conjecture is false. However, there are many cases in which we can use our discrepancy inequalities and kind of the techniques we've developed to show that this is true. So certainly for collinearity graphs of partial geometries, which appear in this kind of claw bound, we can show that it's true. And also graphs where lambda does not exceed mu by too much. So if mu equals 2, we can prove it if lambda over mu is less than or equal to 2, and otherwise we can prove it if lambda over mu is less than or equal to 3. There's still that still leaves a lot left that we're trying to get it for. But so if anyone's ever interested in chatting about strongly regular graphs, perhaps this is a place to find people. I would appreciate it. Right. So what's the overall theme here? I will wrap up. And as I say, using eigenvalues of graphs allows one to understand many, many properties of graphs. And I come from kind of the more analytic bend of spectral graph theory, as it were. So a lot of these things that I like to think about are of this ilk. But it allows one to understand, for instance, diffusion of random walks and things related to the diameter and how pseudo-random the edge set looks, and understand things about the connectivity of my graph and how many subgraphs I have of various types, all of these kind of things. And now what I want to say is that these notions of curvature that have been developed allow you to understand many of these same properties, but coming from much more of a local perspective. So you can understand heat diffusion and therefore random walks by first understanding them locally through this Li-Yao inequality, which kind of tells you how the heat evens out at each vertex. And then you can kind of integrate this between different vertices at different times to understand the diffusion of heat more broadly. You can understand things about like the diameter of a graph. Here again, the arguments are coming from this analytic side, from this heat flow. But also it allows you to understand many of these other things. So you can understand how the edges and kind of balls of radius 2 in your graph are distributed randomly. You can turn this into understanding kind of local connectivity of your balls of radius 2, and also global connectivity, so long as I already know that my graph is connected. And finally, I can also understand things, some subgraph counts. And I think that there's a lot more to come. And I think that my time is up. So I will say thank you. And yeah, thank you.